Okay. Let's start. So we are very happy to have Zhuofeng He from BIMSA to give the last seminar talk this year.
The last one.
Last one this year.
This year.
But actually, probably this semester because
When
we'll
will
have
the first one?
probably this semester.
When will the first one?
I don't know. I actually have no clue because in January we will have a lot of conferences.
At the beginning of
and then we will have our winter break. So
I see.
Next one will be probably in late February.
Okay.
So
okay.
Yeah, for a long time we won't
I
see each other, but
I see.
Yeah. But anyways, we have Zhuofeng He to tell us about certain C-star dynamical system. Let's welcome.
So thank you very much. Many thanks to Professor Wang and for other organizers of this seminar. So I'm very glad to present a talk here and to have this opportunity to talk about some concrete C-star dynamical systems. So basically, I'm going to talk about actions on rotation algebras. So this is what I mean by C-star dynamical system, this class of C-star dynamical systems. And I'm talking about this study in the context of classification of C-star algebras. So probably for the audience of this seminar, it's better to start from the result by Alan Kong of his work of classifying Von algebras, so this kind of separately acting injective factors by the invariant of types and flows of weights. And so in history, so the philosophy of study of Von algebras is often borrowed to that of the C-star algebras, and especially this classification work and has so this is actually the second theorem is a summary of many works by many mathematicians and for many years. So so basically so you can see the statement of this theorem is kind of parallel to that of Alan Kong's result. So this separable simple nuclear C-star algebras that is Z-stable and satisfy the UCT are classified by the K-theoretical data and traces. So so this classification is complete. So that means the invariant, that is the K-theoretical data and traces, often referred to as the Elliott invariant, completely classify the isomorphism class of the C-star algebra, satisfies the conditions as the assumption of this theorem. So separable means that this C-star algebra has a countable dense subset, and simple means that it does not have any non-trivial closed two-sided ideal, and nuclear is so basically, well, so you consider the tensor product of this kind of C-star algebra and other C-star algebra. So there is only one choice of the completion of the algebraic tensor product, and this calligraphy that stands for special kind of C-star algebra. So this C-star algebra admits the same K-theory with that of the complex number. So if you want to classify the C-star algebras by this K-theoretical data, then you have to require that the C-star algebra is Z-stable, meaning that so this C-star algebra absorbs, I mean, it's isomorphic to its tensor product with this specific C-star algebra Z. So this C-star algebra was firstly introduced by two Chinese mathematicians, Jiang and Su. So this is actually called the Jiang-Su algebra. And this UCT stands for the universal coefficient theorem for in the C-star algebraic sense. So this is some computability of the K theory. And you see that the separability corresponds to the separably acting. Injective corresponds to the nuclear, and factor corresponds to the simplicity. So injectivity is the right notion of amenability for Von algebras. Nuclear, the condition for nuclear is the right notion of amenability for C-star algebras. And this Z-stable conditions, that stability well, so it has a counterpart in fundamental algebra, but in this case, it's automatically satisfied. So, and this UCT is something really interesting for sister algebras. And later we will see some example of these kind of theorems of classification result for sister algebras. So usually it's just, well, so of course in practice there are many different variants of classification result theorem of sister algebras. As you might imagine, because, well, so this is actually a summary of many theorems by many hands. But usually it consists of, well, so similar parts. So first you have some conditions imposed to the sister algebra in question. And then the theorem states that the isomorphism class of this special kind of sister algebras is completely determined by this Elliott invariant for this sister algebra. So later we will see one example that applies to our study of the actions on rotation algebras. So let me remind you of the definition of sister algebra. I'm not sure whether you are familiar with this or not. So maybe you are already familiar with this. So sister algebra is just a quadruple that consists of a complex vector space as its underlying set and three operations, one of them binary and two of them unary, and satisfies the following conditions imposed on the operations and interaction between them. So yeah, I mean, so a sister algebra is a special case of many other notions. For example, the condition 1 and condition 4 tells us that our sister algebra is necessarily a special kind of normed algebra, and other conditions gives you more information about compatibility of different operations between them. And among them, most importantly, is the final ones. This is so-called the sister identity. This gives you a really nice structure compared to other notion on the other mathematical object. And examples, well, I'm sure that you're familiar with this. So for example, if you have a compact Hausdorff space, and you can consider all of the complex valued functions continuous on it, and this under the pointwise operation, you have this sister algebra. Norm is just supreme norm. Now, so if you have a Hilbert space, and you can just consider the bounded linear operators on it, you can consider together with the operator norm and well, so the composition of the multiplication and adjoint with as the involution, then you have this as a sister algebra. And the second example, the third example is just the main topic. I mean, so the subject of today's, well, so the underlying sister algebra of the sister dynamical system we are studying today. So this is the rotation algebra. So this is the universal sister algebra generated by two unitaries that satisfies this commutation relation. Well, so governed by this given preset real number theta. So this real number theta is often referred to as the angle between these two generating unitaries. So as you can see from this definition, if we take this angle to be, well, integer, then you have the sister algebra is isomorphic to the function algebra over the ordinary torus, two torus. So that means, well, so yeah, because of this, so the rotation algebra is often referred to as the non-commutative two torus. Now, of course, you can generalize this notation, generalize this notion to any finite dimensional, so just adding more generating unitaries and more commutation relations. You have instead of one angle, you have the whole matrix governing.
So unitary means U1 star equals to U1 star equals to U2. What does unitary mean?
So the involution of the unitary is the inverse.
Okay.
Yes,
one star equals to 1.
Yes, the equation you just mentioned is true, and also equals to the identity operator. Okay.
The algebra is finite dimensional or infinite dimensional.
What?
As algebra is finite dimensional or infinite dimensional.
As a system, as a complex vector space is infinite dimension.
Is there any underlying spaces that this unitary action?
For any system algebra, you can always use the GNS construction to concrete a concrete Hilbert space and get a star representation of the system algebra. Now, of course, it applies to this rotation algebra. So there is a general procedure called GNS construction. So basically, for any system algebra, you have you can prove that there is always a positive linear functional on it. And use that, you can define a pre-Hilbert space, so a pre-inner product on this system algebra, and you take the completion, you get this Hilbert space, and you get a naturally defined action of the system algebra on the Hilbert space. So this is basically the idea of the GNS construction. But of course, it applies to this. Yeah. But for this special case, you might also consider. Let me see. Yes, you can just choose the L2 function on the 2 torus to be the Hilbert space and get a natural representation of this rotation algebra. Yes. Okay. So what is a C-star dynamical system? So this is simply a group action on the system algebra. You have a system algebra, you have a group, and then you have an action. This is the triple. But well, so if in general this group is a topological group, then we need to ask. Well, we need to require the strongly. We need to require that the action is strongly continuous. But well, the system algebraic, the system dynamical system we are talking about today is about the action of integers. So it's we don't need to worry about this. Continuity condition. And whenever we have a system dynamical system, this triple, from out of this triple, we can always define a notion called the cross product. So basically, as the underlying vector space is simply the tensor product of the system algebra and the reduced group system algebra of the group. And then the multiplication is defined by the convolution twisted by this alpha, and then we take the system algebraic completion, of course. And in this cross product, the action of the group on the you have a copy. So we are talking about this discrete group action. So in this cross product, you have a copy of this underlying system algebra, and you have well, so for each element in this group, you have a unitary inside this cross product, and then the action of the group on the system algebra now is realized as the inner action inside this cross product. So this is the reason we want to study this. So the inner action is actually from the adjoint automorphism associated to the unitaries that comes from the element of the group. So this is what I mean. But I just mentioned that in this construction to define this cross product, we need to care about the C-star algebraic completion. So, but in general, we have many choices of norm. So among which we have this full cross product that enjoys the universal property. So for any other choice of the norm, then we have this star homomorphism from the full cross product to the cross product in question. But if the group is amenable, which is the case for our study, so then the star homomorphism is always isomorphism. So we have the full cross product basically is the only choice. Okay, and of course you have we always like the reduced group, like the group system algebra case. We have also this reduced group system algebra. In this case, this reduced cross product coincides with the full cross product. Okay. So basically, I mean that in this case, So you don't have to worry about anything. So the concrete system algebraic dynamical system we are studying is actually out of this as our 2Z action on the rotation algebra. And this action was firstly introduced by Watatani and Brunken. Well, it's defined on the generators in the following sense. It's quite clear. And this is the action of special linear group of degree 2 over the integers. And we can restrict this action to subgroup of this special linear group generated by a single matrix. That is the action of the integers on the rotation algebras. This is what I mean by the class of concrete system algebras. Okay. So, I missed. I should have put the name here. So this result is actually by Riffel, Kimsner, and Voigt-Kolascu. So this is about some characterization of the rotation algebra. So it says that if we are considering irrational rotation algebra, that is the angles that defines the rotation algebra is a irrational number, then the isomorphism class of the irrational rotation algebra is completely determined by the angle modulo the integer and the sign. So this is a very canonical equivalence relation of the angles, defining angles. And also the result also in different papers. The result shows that actually the Morita equivalence of this rotation algebra is also completely determined by determined by the another equivalence for the angles. So this is the this is the action of the general linear group of order 2 of degree 2 over the integers to the angles, and this is by the fractional linear transformation. Yes. And then so this is the joint. So what?
How do you have to do act on?
So this is for any matrix of this form, theta, so this is A theta plus C.
Oh, so this can be a complex number.
Regarded as a complex number, yes.
Okay. So what about rational numbers there?
We will mention the rational case later. Yeah, very nice question. So this is the analogous result, and this is a joint work with Christian, Shanyang, and Hong Zhao. So we consider this action of integers on the irrational notation algebras and studied the isomorphism class and the Morita equivalence class of the resulting cross product. And it's completely analogous. If we have if we are restricting our attention to rational notation algebras and have two generating matrices of the infinite order. So this is infinite order is with respect to the matrix multiplication. Okay. So then the following then the isomorphism class of the resulting cross product is completely determined by the canonical equivalence class of the angles and the canonical equivalence of the related matrices. So this means that this matrix and this matrix has the same Smith normal form. And you might ask why this is this matrix, this identity matrix minus the inverse of A, and you will see the reason later. Or let you know that. And similarly, the Morita equivalence class of this resulting cross products is completely mean by, well, so this equivalent class of the angles and the same equivalence of the related matrices. This means that these two matrices have the same Smith normal form, and this is exactly the statement in the previous theorem given by Pimstern-Boyk, Lasku, and Riefel. Okay. So I will not introduce too much details, technicalities of this proof, but let me just mention the strategy of it. So first of all, I mean, so the proof is actually based on the power of the classification result of C-state algebras. So first of all, we need to show that the classifiability of the resulting cross product. So basically, we need to check all of the assumptions in the classification result I mentioned at the beginning of this talk. So that is kind of separability and nuclear or something like that. And this is indeed the case because this action has a very nice property. So that is called the Trichel-Rohan property. So what I want to mention here is that, so this kind of, so this is another direction of research, okay? So this is about some good properties of the action of the C-state dynamical system, so that, so the good C-state algebraic property of underlying C-state algebra will just pass to the resulting cross product. So this is another direction of study. So there are many more advanced results on this direction, in this direction. And you can find variants of properties of, well, it's good properties for C-state dynamical systems, Rohan property, different variants of Rohan property, Rohan dimension, and so on. It's a very fascinating direction of research. But for the subject today, so this Trichel-Rohan property is enough, and the classifiability is the proof of the first item is really just by gathering and combining the existing result after verifying this Trichel-Rohan property of this C-state dynamical system and apply those results, and immediately you get the classifiability of the resulting cross product. And because of this, because and after the item one, then we can just apply existing classification results, and the rest of the work is just by computing the explicitly computing the Elliott invariance. That is the K-theoretical data matrices in the statement of the result. And it is possible for this case because, well, essentially it's because that, so the K-theory of irrational notation in algebras is well understood. Using that, we can, and together with this, you see that actually, so the definition of this action, this C-state dynamical system is quite concrete. And because of that, so it's quite, it's possible to compute the Elliott invariant explicitly. And once this is known, then by the power of the classification result of C-state algebras, we can prove the theorem I just mentioned. Okay, so the first item is about, so the first theorem is about the classifiability. So basically, you see that the conditions here, so it's many adjectives. So the conditions here just matches the assumption here, and it looks similar to the assumptions in the classification result I mentioned at the beginning of this talk. So essentially, you see that actually, so we need, and for the classifiability, we need to require this signal to be irrational, and this generating matrix is of infinite order. And then we know that this unital, the resulting cross product is unital, simple, separable, nuclear. Monotrichal means that it has a unique trichal state. So it's like you have a unique Borel measure or something like that. And this trichal rank zero means well, so this is actually this is one instance of the regularity property in the classification result of C-state algebras. For example, so for example, finite nuclear dimension, which is very popular here now, is also another kind of regularity property. But anyway, so after verifying the classifiability, we can apply Lin's result. So this is one instance of the classification result, and that I promised I will introduce. So basically for C-state algebras, so this sub C-state algebras, this class of classifiable C-state algebras, which admits this trivial rank 0 regularity condition. And then we know that so this the isomorphism class of these kind of C-state algebras is completely determined by the Elliott invariant that reads as this. For this special case. So here it means that so the complete invariant is given by the K0 group of the C-state algebra, regarded as a partially ordered abelian group. So this positive cone is a subset of K0 group, gives a translation invariant order, partial order on the group. And this is the position of the class represented by the unit of the C-state algebra, and together with the K1 group as just as another. And this isomorphism means that you can find a group isomorphism between K0 and between K1. But for K0, it must preserve the order structure and the position of the class represented by the unit. And as long as you can find some isomorphism between an invariant, then you have the isomorphism, the C-state algebra. Okay, so next I want to talk about. Very briefly how this explicit computation of the Elliott invariant for the cross product in question is computed. So first off, so in general, there is at least I personally don't know any machinery to calculate the K theory for general system algebras. But for this case, we have this Pimsner-Voigt-Kolascu sequence. This is for the integer action. And also, so this Thomson-Cohn's analogous result for the group for the real action, the action of real numbers. Anyway, so we have this exact sequence, and then you can just write this 6-term exact sequence. So this PV sequence into these two short exact sequence, and you see that. So I didn't mention, but actually, so the K1 group of this rotation algebra is actually generated by the class represented by the two generating unitaries of this rotation algebra. And if you choose that as the base of this abelian group, then this action alpha introduced by this matrix, the representative matrix of this action becomes just the matrix itself. So so you see that actually the generating matrix, the trace of the generating matrix is of trace not equal to 2. Then you have this kernel is actually 0. So this whole map. So you can write it down explicitly. This map is the kernel is 0. And then you have this induced map at the K0 level gives you an order isomorphism between the K0, and then the rest of the computation is really just easy. So for most of the cases, it's quite easy as long as the trace of the generating matrix of this integer action is not 2. Here we need to require that the trace of the generating matrix is not 0 and plus minus 1, because we are from the beginning we're excluding matrix of finite order with respect to the matrix multiplication, and for those cases you only have finite order matrices. The first item says that, well, so in this case, and so maybe I should mention that. So you see that actually the connecting morphism here and connecting morphism here is actually identity map, the difference between our identity map and the induced map at the K level. And that's why, so here we need to consider this matrix. You see that, you see the similarity. So the first item says that if the trace of the generating matrix of the integer action is not 2, and this related matrix is has the Smith normal form. Smith normal form is this form for positive integer h and k. Then we have this K0 group of the resulting cross product is just the free abelian group generated by these two classes. So this so I didn't mention that actually. So here P theta is the so-called the refill projection. So we know that so this is what I mean, that the K theory of this underlying system algebra. Maybe I should write. This is what I mean, that this K theory of the underlying system algebra is well understood. So we know that the K0 group of this rationalization algebra is the free abelian group generated by those two classes. One is the class represented by the unit of it, and the other is the class represented by the P theta. So this is the refill projection. This is a projection inside the system algebra, and defined using functional calculus by refill. But in this case, so we know that this the induced map of the inclusion of the underlying system algebra to the cross product gives you an order isomorphism between K0. So we know K0 is. And from the second short exact sequence in the previous slides, we know that this is true. Okay. And also we have this tracial range computation because we need to characterize the K0 group, the order structure of it. But since in this case, this is a really nice case, we know that, yeah, of course, we need to apply existing result to show this. But we really know that this actually I mentioned this. So this resulting cross product is monotracial. So there is a unique tracial state. So basically, the tracial range characterizes the order structure and the position of the class represented by the unit for the K0. And so basically, item 1 gives the explicit computation of the K theory of the Elliott invariant for most of the cases. By which I mean that the trace of the generating matrix of the integer actions is not 2. Okay. But when it is 2, this is a little bit tricky. So this time, so in this case, this map has a rank 1 kernel. And that means we need to find another projection whose equivalence class gives another generator of this K0 group. But we can indeed do that, and we also know the tracial range. And then what follows, I would just briefly mention how this projection is found. It's actually explicitly constructed. Okay. Well, I don't want to really go to too much details, unless maybe you're not familiar, or maybe you're not really interested in it. But what I mentioned here is just to show that this is this projection P sub A is really explicitly constructed. So so we borrowed the idea of the Olivier Esli, if I pronounce it right, in his thesis. So basically so one part of his thesis computed with K0 this cross product of the function algebra of the ordinary two torus, and he showed that this is true. He showed that this is true, and he constructed this P sub U1 and double, and that one. Actually, he constructed this projection as a 2x2 matrix element, as 2x2 matrix over the function algebra in this way. And this is exactly analogous to the construction of the Riefel projection. Using functional calculus, of course. But the x sub 0 and x1 here are also explicitly constructed, defined in 2x2 matrix algebra of the function algebra over the circle. But I didn't give the explicit form of it because it would be a little bit. We don't really need that. I just want to let you know that these x 0 and x1 are also explicitly constructed. And because of that, we can compute the threshold range, and we can actually borrow this. We can transfer this whole idea to our case, to this cross product for general rational notation algebras. And this projection is exactly constructed in Olivier's way. And because of this explicit construction, we can compute the threshold range. And this is very important because we need the threshold range to characterize the order structure of K0. And then we have this. This is exactly the result I mentioned before, just earlier, but in different form. So basically, you see that the rest of the proof of this result is just the implication from item 3 to item 2, right? If we can prove the implication of the item 3 to item 2, and item 2 to item 1 is really just by the classification result of D. Okay. And from 1 to 3 is just a functoriality of K. But we can prove the implication of item 3 to item 2 because once these assumptions are satisfied, because of the explicit computation of the K of Elliott invariant, we can directly construct the isomorphism between the Elliott invariants using our knowledge of the K group, the order structure, the threshold range. And basically, we just have to work on the generators listed in the previous theorem. So that is the sketch of the proof. Rational case. So after that result, we try to or rather, it's better to maybe it's better to say that we try to see what's happening for the rational case, and for this case we only have a partial result, which is so actually for this case it's quite challenging. Because in general, I mean, so for rational case, the rotation algebra itself is already not simple. So actually, we cannot get a readily accessible classification result. You see that a classification result is quite natural, is quite important in the proof I just mentioned. So that is one. I think that's the essential obstacle. But nevertheless, we can still compute these. It's not really invariant, but this is we can still compute the K theory and the threshold range. Well, that is possible. But for the rational case, now this invariant does not really play.
What is rational? What is rational?
The theta is rational. Rational number. Yes. So previously we are talking about this rotation algebra with the defining angle irrational as an irrational number. Now we want to see what's happening for the rational number case. Now we can still compute this K-theory and trivial range. We have exactly the same statement. And this is because, well, so this actually is a consequence of so this is actually a consequence of the computation, explicit computation of the Elliott invariant for the irrational case, and I will mention later. But as a corollary, we have one direction of the implication. So if you have isomorphism between the resulting cross product, you have these data equivalent to each other in the appropriate sense, but we cannot manage the converse implication because of we cannot make a good classification result. So maybe in this case, in this rational case, this invariant is not good enough.
Even so, you have to exclude the case where field is blue.
Yeah, no, not really, because so here, so we exclude trace 2 case because this is new. I mean, for trace 2 case, there are already some study on that. Yeah. So, and which is compatible with this result. But if for trace 2 case, they have so I think that was worked by Farsi and Watling. They have complete result. So for trace 2 case, they have so the isomorphism class is completely class determined by some other data, but only for trace 2.
Yeah, because trace 2 has a lot of meaning.
Oh, really?
Yeah, but they have special elements. Yeah.
Tell me more about this after.
Yeah. Next, I'm going to ask you a question if this can be generalized to arbitrary surface.
Let me finish. Okay. Oh yeah, so this is the very brief idea of the computation of the K-theory and the trivial range. So basically, we can construct the continuous field of C-star algebras and connect the rational and irrational case. And we have the commutativity of this diagram using the evaluation map. And here we testedly use the Boncon conjecture, but yeah, so let me just avoid it. And because of this, we have this commutativity of this diagram. So, well, so this commutativity forces that the K-theory computation of the irrational case must pass to the rational case. And then the rest of the proof is just simply by mimicking that of the rational case. And yes, and in this case, the underlying rotation algebra might have many trivial states, but at K0 level, so they all coincide. So this is exactly, this is also necessary in the proof for the irrational case, but for the rational case, it's also, so there is no obstacle at the K0 level. So we can really just transfer the proof, the idea of the proof for irrational case to rational case. So, okay, so here is the point I want to make with this example, with this this study of the concrete C-star dynamical systems. So basically, so you see that actually Professor Wu asked me earlier that what's the application of the classification result of C-star algebras. Yeah, of course, there are many directions. But in general, so the classification result of C-star algebras, I mean, the Elliott invariant is very difficult to compute in general case. And, well, but for concrete classes of C-star dynamical systems, well, because it's concrete, you have many other structures. So well, it is possible that for some subclass system dynamical systems. The resulting cross product, the Elliott invariant of it, you can compute it. And once you can compute it, and the classification result enables you to to read out the isomorphism class of the resulting cross product by some really simple or very natural data out of the system dynamical system, just as what we did for the rational notation algebras and rational notation algebras. And you see that actually, so this classification result is really something for the C-stat algebraic sense, because you see that actually for the rational case, because invariant does not really work that well. So you don't have this result. But for irrational case, you have really neat result that characterize the whole isomorphism class of the cross product angles and generated in my case. But there are many other classes of concrete C-star dynamical systems, right? So there are many rich structure out there, and so I think this is one of the direction that you can apply the classification result. And so basically the study of the C-star dynamical systems is from the beginning of the study of C-star algebras. So this is, and also this is the spirit in the study of fundamental algebras. So, so this is the point I want to make with this result. Okay, so I think I will just stop here, and thank you very much for your attention, and I will wait for question comment.
Thanks for the really interesting talk. I believe there are many questions to be raised, but let's see if there's any question online first. Let me stop this recording.